Principles of Operating Systems, Chapter 8, Security, Antivirus, Encryption and Decryption. Our daily lives, our economic safety, even the national security, becoming more and more dependent on stable, safe, and resilient communication systems and computer systems. So computer security is an extremely important issue. Now, what we mean by computer security is system integrity and its maintenance, the availability of information and the confidentiality of the information that computer systems deal with. The operating system plays a major role in overall security of a system. The main security issues that an operating system might deal with are authenticity, availability, confidentiality, and data integrity. One of the functions of the operating system is to provide a level of security, and the system then has to defend against physical malfunctions, user errors, and attacks from external sources. The security within a computer system can be divided into several layers, maintaining security of information that the system has, the physical security of the system, and the security of the network that it's operating in. Of course, the operating system can't prevent physical malfunctions, so its role is going to be limited to the detection of malfunctions when they occur, and physical malfunctions will occur, and limiting their damage to the information in the system. Data storage information is always subject to errors, and so is data transmission. In a digital system, a data error has to take the form of a 0 stored where the correct value is 1, or a 1 stored or transmitted where should have been a 0. These kinds of errors can be due to several things: manufacturing defects, wear, environmental EMF, many other factors. Most operating systems have some kind of error detection, and most of them have some levels of error correction. These techniques enable the reliable storage and delivery of digital data. Error detection techniques, of course, support the detection of errors, and error correction enables the reconstruction of original data that might have been corrupted. Error detection usually implemented by introducing data redundancy. Users then can use the redundant data to check for consistency, and, with some schemes, to recover corrupted data. Often, usually these schemes involve introducing check bits, often in the form of parity check bits. But check bits derived from the data by some algorithm. The user then can use the same algorithm on the data bits, compare the output of the algorithm with the check bits in the data. If the values don't match, there must have been corruption, some kind of error in the data. Many of the algorithms used also support error correction, identification where the error occurred, which bits were problematic. Since a bit can only have value 0 or 1, once you've identified that the value stored is wrong, it's easy to identify what the right value is. If you have a 0 stored and you know it's the wrong value, then the right value must be 1. If the value you have is 1 and you know it's wrong, then the value should have been 0. A parity bit is a bit added to a group of data to ensure that the number of bits in the data that have value 1 is either an even number or an odd number, depending on whether you want to check even parity, odd parity. This is a simple scheme. It detects single errors. In fact, it will detect an odd number of errors. If the data includes an even number of mistakes, then a single parity bit won't detect the problem. A checksum is a modular arithmetic sum of that data. Checksums, modular arithmetic sums, can be negated by a ones complement. When you compute the ones complement and add it to the original data, you should get 0. This is very efficient and easily detects whether the data has an error or not. Checksum schemes include parity bits, check digits, and longitudinal redundancy checks. Some checksum schemes have been specifically designed to detect the kinds of errors that humans commonly introduce when they are making a mistake writing down things or misremembering identification numbers. Error detection and correction codes are used to improve the reliability for data storage. This has been recognized from the very beginning. The very first tape data storage back in 1951 had a parity track for error correction. The ORC optimal rectangular code not only detects errors, but corrects single-bit errors. Can figure out which bit had the error, and of course then it can change it. Some file formats include a checksum. Usually it's a CRC32. The checksum is to detect corruption and truncation and can employ redundancy or parity to recover portions of corrupted data. Compact disks use Reed-Solomon codes. Reed-Solomon codes also get used for DVD and ATSCs, as such stories like RAID 6. And they're used in satellite communication. Modern hard drives use CRC codes to detect minor errors and Reed-Solomon codes for correcting them. RAID systems use a variety of error correction techniques for correcting errors to recover when a hard drive completely fails. Some file systems and some RAID implementations also support data scrubbing and resilvering. Data scrubbing is a technique using background tasks to periodically inspect main memory or secondary storage for errors and correct the detected errors. It reduces the likelihood of a single correctable errors accumulating. It cuts down on the risk of uncorrectable errors. Resilvering, or resyncing, or rebuilding, or reconstructing, is the process of repairing a damaged device using contents of healthy devices. These techniques detect bad blocks and hopefully they can be recovered before they have to be used. The recovered data then can be rewritten, either overwriting exactly the same physical locations if they are pure software problems, or elsewhere on the same hardware or on replacement hardware, whatever is appropriate. DRAM memory can provide increased protection by built-in error-correcting codes. This kind of error-correcting memory, EDEC protected or ECC, is especially desirable for applications that cannot tolerate errors, as well as applications where there are high rates of RAM errors, as in deep space applications where there are high radiation levels. Error-correcting memory controllers use Hamming codes or, in some cases, triple modular redundancy. Interleaving is the association of neighboring bits physically close to each other, using them in different words. The idea is that events that cause errors are more likely to affect bits that are physically close to each other. That way, then, such an event is less likely to cause multiple bit errors in the same word. That makes the error bits, not only easy to locate, to identify, but to locate, and that way to correct them. In addition to the hardware correction system, operating systems have reporting facilities to notify the errors that have been recovered. If the number of errors starts getting higher, it might be an indication that one of the memory modules is failing and needs to be replaced. This kind of feedback information is not easily available if it isn't built in, if we don't have the reporting capabilities. Linux has one, the EDAC subsystem, previously known as Blue Smoke. It collects data from the error checking components in the system. It collects all of the information about the memory correction and also those in the PCI bus. There are a few systems that also support memory scrubbing. Memory scrubbing consists of reading through computer memory, word by word, identifying and correcting any errors that it finds. Now, because of the density, the small size of the memory cells in the computer chips, individual memory cells are small enough to be affected by cosmic rays or radioactive decay particles. These errors, not programming, not built in, these are soft errors. And over 8% of the memory modules will have at least one correctable error per year. This can be a problem for large systems, especially large sensitive systems. The probability of an error in any individual bit is very, very small, but a given computer will have a lot of bits, and computers can be running for a long, long time. That means that the probability of an error in a given computer is significant. Now, information in memory is the modules are designed for enough redundancy to correct single bit errors, and that is generally good enough to support scrubbing as long as it is done regularly. If the memory controller scans systematically through the memory, single bit errors can be detected, the erroneous bits can be identified, and the bits corrected, the correct values written back into memory. One of the most important aspects for an operating system is to allow the system to continue operating even when errors have occurred, or to resume operation after errors have occurred. There are lots of techniques that have been developed to facilitate error recovery. They've designed, first of all, to design the system to be able to operate without some of the hardware components. If something fails, the system can still continue functioning. Of course, it's essential to be able to identify when an error has occurred and to correct the errors after identifying that they have occurred. If you store multiple copies of essential data and put them in separate locations that are unlikely to suffer simultaneous damage. If you have computer files that are extremely important, then you should have a backup process, a system for creating these copies as a protection against disasters that can destroy the files. To back up a file just means make a copy of the file and put it in a different location so that you can restore it if something happens to your computer or if somebody accidentally deletes the file on the main computer. There are lots of ways to back up for files. Most of the computer systems have utility programs to help in this backup process. Of course, this can be very time-consuming if there are a lot of files. If you're going to put the copy in a secure location, then it has to be on a medium that can be removed from the computer. Writable CDs, cartridge tapes. You can also copy files to another hard disk, but if the hard disk is on the same computer, you're protected against failure of one disk, but of course, it's possible for the entire computer to be destroyed. So if it's that important, you should have copies of the file or in some removable media and stored in some distant location, safe. Technique that has been developed is a grandfather, father-son backup technique, making 3 backups. We have the current copy, working copy, a most recent backup, the father, and then a backup of the backup, the grandfather, in an even more secure location.